Even though I ate like 5 this morning. Oh my gosh.
Okay. So let's continue and finish up moisture analysis. Okay. Oh, +2. I remember to bring that with me next time. All right. Okay. Well, so Wednesday beat Monday. That's time. Last week, everybody got +2. I even tried to convince the TAs against giving everybody +2. Like, are we now giving everybody +2? Yeah. So, anyway. Good job. I think we have one group that got +2 every week. Not naming names. Okay. All right. So, couple of recap questions. What are some methods for measuring moisture content? All right, come on.
Microwave oven.
Microwave oven. Mick. Huh?
Carl Fisher.
Carl Fisher. Why do I always want to call him Mick?
It's you can call whatever you want.
Force draft. Okay, so vacuum, force drive, Carl Fisher. So the oven methods, Carl Fisher, we have like many methods. The rapid moisture analyzer, infrared analyzer, and so many. Direct and also indirect. Can you name one indirect method? Very common, Sierra. Yes, absolutely. It is NIR. I'm not sure if I would call it indirect. It needs calibration and it's measuring the OH groups of water. So yeah, it'd be indirect. But I was thinking of something else, really. You tend to use hydrometer is one. The one I was thinking of is refractive index because you measure total solid, and by that you get the moisture content. But yeah. So what are some considerations and errors for oven drying method? Let's name a few. Definitely. What's that? Chemical reaction. Can you think of an example? Maillard reaction. Does it cause underestimation or overestimation? Overestimation because it's condensation. You lose water that is chemically bound and you evaporate it. Okay, what else? Consideration. Lipid oxidation. What can it cause? Over or under? You gain oxygen from the atmosphere. So you get more quicker solids, so you underestimate. Yeah. Loss of volatile compound that causes under or overestimate. You have less solids remaining. Over. It's always tricky because it is you are subtracting. Anything else you can think of? We don't want to form a crust, for example. We use sometimes if a sample is prone to form crust, we use sand to kind of disperse your sample. Using glass wool to avoid samples blowing off, especially in forced draft oven and so many other things. So you can review. Okay, so be ready to, in an exam, just give me at least three considerations of potential errors. Examples. Okay, So very quickly about moisture sorption isotherm. So it is the relationship plot between moisture content on dry bases, which is the ratio of moisture to dry matter, in relation to water activity. So it gives us an indication at equilibrium. So we have to reach equilibrium to measure the actual water activity at equilibrium under different relative humidity. So it is impacted, as you see here, it is impacted by, okay, it is impacted by the affinity between water and sample. So how much the sample components have tendency to interact with water and how much water is potentially going to be lost or gained. The temperature is a factor, relative humidity, surface area. So the higher the surface area when your sample is finely ground, the more movement in water you're going to see. We call it desorption and resorption and desorption. So desorption is losing water to the environment, resorption, gaining water from the environment. So the isotherm will be impacted by these characteristics. And usually we determine the isotherm at equilibrium. So we used to, in the past, as part of your moisture lab, we used to plot isotherms. So the way we used to do it is we used to take one food product, baby cereal, and we used to store it at different water activities and allow it to equilibrate for about 3 weeks. Let me take that out of the way. So, and at different water activities or relative humidity, 7 different relative humidities, and we let them equilibrate for 3 weeks. During that time, the moisture of the sample and the water activity of the sample reaches equilibrium. And we measure moisture content and water activity at each of the 7 relative humidities we stored the samples at. And we plot that, plot the isotherm. GAV or gap is the most common representing the sample across different many water activities, a wide range of water activities. So it is not a linear relationship, and it allows you to calculate the monolayer, the moisture content at which you have maximum stability, and it allows you to predict the stability of the sample and the onset of chemical reactions or microbial growth. Traditionally, we would store samples in desiccators, and underneath that plate here, we have salt solutions. Salt solutions that will give you an environment with a specific relative humidity. So in lab, we used to store them at, like I said, at 7 different water activity ranging from 0.11 to 0.85. And let them equilibrate in a desiccator for 3 weeks, like I said, and then we take a sample from each water activity or relative humidity desiccator, measure moisture content on dry bases, which is the ratio again of moisture to dry matter, and plot it against the water activity that we actually measure using the Depicon, like we did in lab. And then we plot the desorption, the loss of moisture, and the sorption, which is the gain of moisture. And from that plot, we used to have a big Excel sheet that will calculate the monolayer, multi-layer of water, and a lot of different mathematical calculations to help you understand the stability of your sample as well as the shelf life of the sample. You could have an automated way to measure isotherm instead of incubating the samples for 3 weeks, reaching equilibrium, and then measuring moisture content, and then measuring water activity. There is an instrument that can call it dynamic instrument because it measures measures the water activity and moisture content, and it changes at different relative humidity. So itself, it will change the relative humidity. It will allow equilibrium, and then it will give you the data and plots an isotherm. We don't have that. We don't have this dynamic vapor sorption, at least now that as far as I know, we didn't have it. So in lab, we used to do it by actual incubating, waiting for equilibrium, and doing it by hand. So that's it. What do I want you to know about isotherms is how do we develop an isotherm? Making sure you have constant temperature, let the sample reach equilibrium at specific relative humidity, measure moisture content and water activity after equilibrium, and then plotting and amplifying and applying the gap equation, which you don't need to know the mathematics behind that, and then calculate the monolayer and predict the shelf life of the product. Okay, what do you need to know from isotherm? Sure. So to plot an isotherm, you want to have your samples equilibrated at different water activity variables. After you have that equilibrium, what do? You measure moisture content on dry basis, which is the ratio of moisture to dry matter, and you want to measure water activity. And then you plot the relation between water activity and the moisture. And you use mathematical equations. Usually we use gap, GAG, to calculate the monolayer and determine the moisture content at which your sample is most stable and predict.
Did you say what gap stands for?
Not really, I didn't. I don't even, it's the name of the people that developed it. GAB. So it's a combination of, there's so many equations, and all of them are related to the names of the people that came up with. Yeah, so I didn't say what it stands for, no. But it's mathematical relationship that is non-linear. On this slide, I think somewhere I put BET equation. BET is linear relationship, and usually it's only accurate between 0 to 0.5. Gap is accurate prediction over a wider range of water activity. I won't ask this question, but I'll just let you know because you asked. So BET based on the name of the people, and BAB also name the mathematicians. Okay, Rachel, did you get all of that? What do you like me to repeat? Any? Okay. All right. Okay. So that concludes moisture content. Okay. Okay. All right, ash is the next component in the proximate composition of food products. You will be running ash content next week in lab. You're also going to be doing a fat analysis. So I don't know if I'm going to get to the fat lecture today, but I will, not on Monday, on Wednesday, because we have an exam. So what is the definition of ash? What do you know about ash? What is it to you? Go ahead, Sumili. Oh, sorry. Sumili had her hand up. What is it?
It's just, uh, they're leaving behind the inorganic.
Yes, very good. What were you saying? Similar thing? Okay. So the definition of ash is anything that remains after you burn off organic matter. Everything that remains after you burn off organic matter. So inorganic matter is what remains, and mostly it's the mineral content. So many years ago, I don't know what I was thinking, but I wanted to animate it. It's like, so this guy apparently is the organic matter. And this guy is burning everything. This one is running out. We got inorganic matter. Not sure why I did that, but maybe I was bored one time. Okay, well, it at least gives you an illustration of what happens. Sash, what? I don't know what I searched for. This is many years ago. I don't know what was I thinking, but okay. So your organic matter will burn off into the gases. So CO2, NO2, SO2, because we have sulfur in the protein. So NO2 comes also from nitrogen containing organics, CO2 mostly from carbon containing organics. And what else goes off during fasting? I just taking a picture of you can. What else? The sample. So yeah, so everything is gone, and then you have mostly minerals. You want to see white ash. So the ash, when it's white, you know that you burnt off everything. If you have a little bit of gray or black color, that means you still have some carbon. But sometimes, no matter what, some samples remain gray. So does camelina and pennycress remain gray? Yeah. Yeah, so it never gets to really that white. So there must be some inorganics there that doesn't really turn white. Yeah. But in general, you want to see the gray and black gone, then you can say the ashing was complete, with exception of few samples. Okay, so what's the importance of ash analysis? Why do we do that in food analysis? Why do we care about ash? Determination of ash content. Why do we determine ash content? Yes, we need the ash, we need the moisture to calculate carbohydrate by difference. Okay, what else? Anything you can think of? What did we do for AA? You have to ash the sample to determine, yeah, determine mineral composition. The first step for many foods, or most of the foods, is get this organic out of the way so that you can determine ash content. So I really was just feeling bored that day. Okay, so as part of proximate analysis for nutrition label, oh, that guy. Do you know Popeye? The sailor man. Toot toot. It's Friday, Sal. Let me tell you. Okay, yeah. So he used to get strong when he eats the spinach because of the iron in it. Okay, so preparation step for specific element analysis. So these are mainly the two reasons we do ash content. Also, it's not here, but it's kind of a quality measure. I used to work in a flour mill in the R&D lab. And I used to run IR all the time on the flour that comes out. And to evaluate the level of refinement. So it has to have a specific ash content to meet the requirement to say this is a refined flour. So most of the brand and associated minerals are no longer there. So is another reason for measuring ash content as its quality parameter. We also measure ash content in our lab quite a bit. Why? So, why do we do ash content in our lab? For protein, extracted protein.
Oh. So. Yeah, really sorry. Like when we are extracting the whole.
Yeah, so when we extract protein in our lab, a lot of time you have to add, increase the pH, reduce the pH. So when you add NaOH and then add HCl, what are we creating? NaOH plus HCl gives you NaCl plus water, right? So we're increasing the salt content. Salt is not really good if you have high salt content in ingredients. So we measure ash content to determine if our process in removing the salt was successful in isolating the protein. So again, quality, not only for these two reasons, but also for quality measurement. All right. So how do we prepare the sample? So those of you that have cheese products, so cheddar cheese and Parmesan cheese, it's a relatively high moisture products and also high fat products. So all of those of you that will be doing ash content in cheese, you will get a dried sample, a pre-dried sample. Because if you don't have a pre-dried sample, you get splattering, swelling, and then things will come out of that little crucible and you lose sample and you underestimate your ash content. So you want to dry high moisture sample before you put them in the muffled furnace at very high temperature to ash them. So your cheese samples will be freeze dried. You can also dry them by vacuum oven to remove the moisture content. And then you're going to calculate ash on dry basis. Rest of the samples, all of your like cereal products and almonds, we don't pre-dry the samples. And now fat content will impact, also might cause loss of sample during ashing. So if you have high fat content and you put your crucible in the muffled furnace, yeah, oven that works at high temperature called muffled furnace. So if you put the sample at really high temperature, the fat will cause smoke, and also some of the sample will be lost as well and cause underestimation. So what you're going to do in the lab, your dried cheese samples, when you weigh it in the crucible, you're going to put it a little bit on the hot plate and smoke off the lipid. So remove all the smoke so that you don't have a lot of smoke generated in the muffled furnace. Although all muffled furnace should be under an exhaust system, but if there is a smoke, it will be contained in the exhaust system. But a lot of smoke can potentially lose samples because of the potential movement of the particles when the smoke is generated. So you don't want that. So some samples require drying and smoking the fat off. Okay, sugar products with high moisture content can cause foaming. So that's why we also want to dry and also to smoke it off because of the charring that could happen because of the sugar. All samples is recommended for you to mill or grind. So you have them in a powder format. However, if the grinder that you use has metallic form, it might contaminate the sample. You might have higher iron in it in your sample than should be. So it could be a source of contamination. So we need to be careful what grinder we use to avoid contamination. So ashing method, the most common method is dry ashing, but sometimes we do wet ashing as well. So we're going to talk about dry ashing and versus wet ashing, and then briefly at the end, I'll talk about microwave ashing, which takes much less time to get your ash or burn off your organics. So in dry ashing, we use the muffle furnace. Like I said, it is a kind of it's an oven, but can reach really high temperatures. So usually we ash anywhere between 450 degrees C to 550 degrees C. So that's really high temperature, and that's the average of the temperature that we usually use. At this temperature, all of your organic will oxidize and evaporate as gases, NO2, SO2, CO2, and the moisture, obviously, as H2O vapor. There are a lot of different types of crucibles you can use, but the most common and the one that you use in the labs, it's the porcelain. It has good resilience to temperature, but the only problem, it cracks. It can crack if you have a sudden change in temperature from cold to hot. Usually we put the samples in and then we turn on the muffle furnace. So we have a gradual increase in temperature. And also it is stable with acidic food, but not as much with a high alkalinity food. Quartz, this is quartz. It also have similar stability to porcelain. It is more expensive as well, so we don't see it much in labs. Platinum is the most inert and the most expensive. Steel is cheap and it's stable with acidic food, neutral food, alkaline food. But the problem with steel is you might have contaminants like nickel and iron in your sample. Quartz fiber is made up of quartz material, but a fiber that is porous. So it allows you to heat at really high temperature and good circulation of heat. So you get reduced time for ashing. Okay. But you will be using porcelain in the lab. So dry ashing, the advantages, it's safe, well, relatively. You don't want to put anything flammable close by if it is on. And also you don't open it if it's hot. What we usually do is we put the samples in when it's cold, close it, turn it on. And then when you're done, you turn it off to cool down before you take the samples out. You don't open the muffle furnace when it's really hot. You don't want to do that. But if you follow these rules, it is generally safe because it doesn't have any reagents. You don't need to monitor your samples. You just put them in and come the next day, turn it off, wait for it to cool, take it out. So nothing really needs to be done other than weighing accurately your sample. And depending on the size of the muffle furnace, you can put in a lot of crucibles and do a lot of samples at one time. It's disadvantage to get the equipment, it's expensive, and to ensure that it has a hood over it. Yes, Rachel. Yeah. Not pure sugar per se. you can do pure sugar if you want to. You're putting nutrition label in a pure sugar, but sometimes you have products like sweets have a lot of sugar in them. So, and you just need to do ashing for nutrition label. Yeah, jams, jellies, high in moisture, and also sweets like candy, high in moisture and high in sugar. Yeah, if it's high in moisture, you freeze dry, but also you try to char them on a lower temperature, like on a hot plate, so that you don't get that charring happening and particles go off from your little crucible and you don't underestimate. Good. Okay, so disadvantages of ashing, it's a lengthy procedure. Usually we put it close to 24 hours overnight. And it is an expensive equipment once you buy it, but once you have it, and it really lives a very long time, very low maintenance. But the main disadvantage, if you want to do mineral analysis, and especially for nutrition label, if you want to do iron, you're going to have to do wet ashing because the iron evaporates. It's a volatile mineral. Oftentimes, if you want to get an estimation of iron, you combine dry ashing and wet ashing. So what Cindy and the TAs did for you for preparing your ash is that they ash for a while, take it out, add a little bit of nitric acid to kind of enhance the oxidation of the organic matter, and then put it back in the oven or furnace for a controlled period of time to limit as much as possible volatilization. But who got underestimation of iron in the lab, for those of you that did the AA? On cereals. Cheerios, and did you do the lab report or not yet? Cheerios and baby cereal. Did you get the lower iron content? No. High? Higher than the label? Well, that's a first. For both products? No. Such? Can you compare? Look. Cheerio underestimated. Usually, almost every year, we have an underestimation of iron because of volatility. I don't know if this year was unique. Somehow we didn't lose iron. But it's common that using dry ashing, and if you want to determine iron content for nutrition label, you will underestimate. So you would need to do wet ashing, and I'll talk about wet ashing in a little bit. All right, so what are some sources of error that you think can happen for dry ashing? We did talk about a couple that could be error. Yeah, charring, or the water splattering, loss of volatile minerals, contamination. Another common one is incomplete combustion. So your ash, if it's not white, and your sample doesn't always give you a white color, so you don't know really if you have completed the combustion or not. If it's not a complete combustion, you will get over or underestimation. So this is different than moisture, right? So the organic matter leaves and you weigh the ash content. If you still have organic matter, you overestimate your ash. If you lose volatile minerals like iron, zinc, copper, phosphorus, you get underestimation. The weight will be less. So these are, sample not represented. This is a problem for everything really when you do analysis. If you don't have a homogeneous sample and you did not have a representative sample of the whole population, that will always give you an error. So that's a safe bet when I tell you what's the sources of error. Is sample not represented? Contamination due to milling in a metal container. Loss of sample during drying before ashing. So, yeah. Okay. Pull out a piece of paper, write your name on it, and then you'll do a couple of calculations for a +2, and you'll give those to Nigel at the end. Okay. So try to solve for ash content on dry bases. So the information here, you have a hamburger sample. It has 47% moisture content. It has 56.6% fat on dry bases. So that we're complicating things. And then we have 1.14% on wet bases, ash content. How would you determine percent ash on dry bases? So take a moment and solve. Okay, anybody? Or not yet? Do you have it?
I think it's 2.15%.
Yes, it's 2.15%. How did you do it?
Uh,
What did you calculate
I
first?
used the wet basis and then I divided it by 100% minus the 47%.
Yes, times 100. Yeah, okay, correct. So what Tyler did is determine the dry matter. So what's your dry matter? So the dry matter is 100 minus 47 because this is your moisture content. Okay, so the dry matter is 53%. That's your dry matter. When we say calculate on dry basis, so the amount that you have on wet basis relative to the dry matter times 100. So you have 1.14% divided by your dry matter percent times 100 is what gives you 2.15. All right, attempt the next one. So before you attempt the next one, what did you notice? So you have 1.14, that's one on wet basis. This is on dry basis. What do you note if you compare this to this? What's your observation? Your simple observation, it's higher. Your dry basis is always higher than your wet. So if you want to know if you did your calculations correctly, the dry basis content is always higher than the wet basis, because you're taking away the moisture and you're just looking at the ratio to the dry mass. Next. So that's the next question. What is the ash percentage on fat-free bases? Not on dry bases, on fat-free bases. The reason sometimes we need this math, because instead of what you're gonna do in the lab for cheeses, burn off or smoke it off, sometimes they dry the cheese, defat the cheese, and measure ash content. Then you need to know how to convert from that to the whatever ash content you have in your sample and vice versa. So it's not, I'm not being creative in that question. It's just, it does happen in analysis that you remove the moisture, you remove the ash, sorry, the fat, and then you determine ash and back calculate. All right, so think about it for a minute and then I'm gonna ask you, what's the first thing you wanna do? So think about it for a minute. So what is the first step? So what do you see here? We are giving you fat content on dry basis. Now, you really want it on wet basis. You want to get the fat content on wet basis. You want that value because what I'm asking here is ash on fat-free basis, not on fat-free dry basis. So what would be the percent fat on wet basis? Anybody determine fat on wet basis or how we would do it? how do I go from dry to wet? You need that calculation. You need to know this calculation, especially next week in lab. You're going to be determining fat content and ash content in cheeses that we have dried for you. So you will determine them on ash, yeah, why don't you confuse us, Pam? Let me rephrase. So next week in lab, all the cheeses will be pre-dried for you. When you run ash content and fat content, the values you obtain are on dry basis. You need to know how you're able to convert them to wet basis. So that's the importance of knowing this. So you're obtaining the fat content on dry basis because hamburger also has a high moisture content. So we did determine fat content on dry base. So in this case, you have, anybody done it or no? We give up. Anybody got the value? No? So what's your value, Mara? Huh? Is that fast? Yeah, it's a little low. It's a little low. Okay, so you have 56.6%. So you have 56.6%. So you have 56.6 grams of fat in 100 grams of dry matter. Does that sound right to you? Okay. So you have 47% moisture. So in your actual wet sample, how much is your dry matter? 53. So I want to know how much of that is that 53? Yeah, dry matter. So how much of that dry matter is actually fat content? So I would multiply this by 53 over 100. So what is the value that you get? You're basically getting how much fat you have in your dry matter fat. 53 in 100. So what was the calculation? What is the percent fat on what basis? 30%. Just this fat. So 30%. So now your fat content is 30%. If I want to determine my ash on fat-free basis, so I want to remove from the 100%, I want to remove the 30% fat. Remove from the 100% of my sample, I want to remove 30%. I have 70% of my material doesn't have fat. So 70 grams and 100 grams don't have fat. I remove the 30 grams fat. So now my ash content is 1.14% on wet basis. I'm not calculating on dry, I'm calculating on fat-free basis. So times 100 over 70. So I want to know the relative value of ash to a sample that doesn't have fat. So 1.14 in the relative value of 70, what would that be? 1.14 times 10 over 7. What do you do? 1 point. Okay. Very good. Time is up. Yeah, I have few slides. I'll finish them on Wednesday. It's all about what ashing. It's okay. All right. Well, study well for Monday. And if you have questions, you can send me an email. Yeah, can you confirm with Brittany? You should have gotten the MSP put up. So I think the MSC was put up because Wednesday was the deadline for the other group. And today by midnight is the deadline for AA. So it should be up tomorrow. If you don't find it, email me and Brittany. Yeah.
Yeah.